The year was 1903. It was a gray, gusty Thursday at Kill Devil Hills, when Orville Wright took to the controls of the flying machine he and his brother had designed, built, and aptly named the Flyer. When the signal was given, this 40-foot wood and silk contraption left its earthly bounds for a grand total of 12 seconds, while traveling 120 feet at almost 7 miles an hour. Of course, we all know what happened next. But hold on, instead of going forward, I want to go back, because before this could happen, something had to be invented. Of course, we needed the internal combustion engine, but more importantly, what's attached to it, the propeller. The concept of a propeller dates back to 1882, when Schuler-Wheeler decided to take an electric motor and pair it with an angled blade. Yep, this was the world's first electric fan. By definition, a powered machine used to create a flow of air. The concept was the same as fans as far back as ancient Egypt, basically moving air by propelling it with some other object. But now that we had the propeller in a fixed, control rig, we could get better at determining the right angles and ways to force air to move. We even got smart and mounted the assembly on the ceiling, calling it a whole new invention. Eventually, the Wright brothers took this idea and used it to propel their Flyer through the sky. And the whole thing goes in a complete circle, because the science and ideas set into motion by the Wright brothers in developing airfoils and wings also ended up advancing the field of fans. So today, we'll go through some of these concepts and how they pertain to fans of different kinds. And to do so, we'll have the help of industry experts like Bill.
If you really dig into it, there's a lot of different ways to move air. As a young engineer, that was one of the things I was kind of blown away by. You know, you have upblast fans, downblast fans, centrifugal wheels, axial wheels. Each one of them has a very specific purpose, and it can be a little bit confusing sometimes. Hopefully this helps clear some of those issues up. When you boil it down to the fundamentals, essentially what fans do is move air.
But how do they actually do that? What makes the air move? It's all about pressure. And what fans do is create what's called a pressure gradient, or a pressure difference before and after the fan. To demonstrate, here's a small fan inside a duct, and 2 ping pong balls exposed to the duct. When I first turn the fan on, the balls stay in place. And that's because right now, this duct is fairly open, so although a pressure delta is developed and air is flowing through, it's not enough to affect the balls. To raise the pressure, I'll now restrict the exhaust side of the duct, and there you go, the right ball moves up. This tells us that by restricting the exhaust, we developed more positive pressure on this entire side downstream of the fan, enough to push the ball up. But notice that this had no visible effect on the ball on the left, the intake side. So now let's restrict that side. Now that ball goes up. By restricting the intake, we decrease the pressure upstream of the fan. So the ball got pulled up by the vacuum, right? Well, I think that's the most common way to explain this effect, and I'll even probably say fans pull air somewhere else in this video. But here's the most complete and correct explanation. Our atmosphere at sea level has an average pressure of 14.7 psi. This is psi absolute, and would equal 0 psi on, say, your car tire gauge. What the fan does is just create a low pressure by its intake. And since we closed the restriction, the pressure inside this duct decreased to below ambient pressure. Air always wants to equalize and move from a higher pressure to a lower pressure. I think that's intuitive. So it's the ambient air that pushed up on this ball, rather than the ball getting sucked up by the fan. The same goes for the air entering the intake. There's a low pressure here, so it wants to enter. And even for the exhaust side, we raise the pressure in this duct, and so the air wants to escape to the lower pressure of the atmosphere, giving us a constant airflow through the fan. Now, so far I've just been calling these pressures, but now is probably a good time to make the distinction that with fluids in motion like the air here, we have 2 kinds of pressures. We have static pressure and dynamic or velocity pressure. Let's look at static pressure first, since that's what the ping pongs were demonstrating. Static pressure is the pressure exerted by a fluid when at rest. But what does that mean? The air is moving, so how can it be at rest? In this case, our static pressure gauge, the ping pong ball, is exposed to the duct, yeah, but it's not really affected by the speed of the airstream, because the speed is virtually all in this direction. There is no speed going up to push the ball. But what there is a constant static pressure on the walls of the duct. So anywhere we measure along these walls, we should see the same static pressure. It's like blowing up a balloon. When at rest, we only have static pressure against all the walls of the balloon. Then when we open it up, we start to lose some of that static pressure as it's converted to velocity pressure. And that's the other half of the equation. Velocity pressure is pressure exerted by a fluid because of its motion. We already visualized it when we first turned the fan on. It moved this flap up a bit, and that was purely due to the velocity of the airflow. Here's a shot with some smoke where you can clearly see there's a lot of kinetic energy in this airstream. But I think this is almost as far as we can go with ping pong balls, so I've put together this little demo to really visualize the difference between static and dynamic pressure. We have a fan on the left moving air into this duct, and within it we have two pipes. The pipe with blue water measures the static pressure within the duct. Notice that again, the pipe is at an angle such that the speed of the airflow will not really affect the reading. It will just be the static pressure that normally pushes out on all the walls of the duct that will make its way into the pipe and push down on the column of water. We'll then measure how much the water column rises on the other side in inches to give us the static pressure in inches of water column. If you ever wondered exactly how inches of water column works, this is it. So let's turn on the fan and see what happens. Well, it looks like our static pressure hasn't changed a whole lot, and that's because right now this duct is pretty open back here. But this red water column has moved up about 1/4 inch, and this gauge is indicating dynamic pressure. Sort of. You can see that this pipe is angled in a way that it will pick up the speed of the airflow moving within the duct. The kinetic energy from the air will travel down the pipe and push down on the column of water. However, the pipe is also exposed to the duct just like our static pipe, and so this static pressure will also have an effect on the column of water, meaning the red gauge is actually going to represent the total pressure in the duct, which is the sum of static and dynamic pressures. All we have to do to get dynamic pressure on its own is subtract the static pressure reading from the total pressure reading. And right now, since the static pressure is at or near zero, the total pressure reading is basically our dynamic pressure reading, and it looks like it's about 1/4 inch water column. But how is this dynamic pressure useful for us? Well, the cool thing about dynamic pressure is that it's related to the speed of the airflow. And if you know the cross-sectional area of the duct and the speed, you can calculate how much volume of air is moving in cubic feet per minute or whatever other metric you'd like. But for this demo, we'll skip the calculations and just look at the relationships. So let's start restricting the duct to see what happens next. At this point, we've added just a bit of a restriction, and the static pressure went up a little bit, as did the total pressure. But did they go up equally? No, it looks like static pressure went up just a little bit more than the total pressure. As I restrict the duct a little bit more, pay attention to how these columns move. And I know it's not totally obvious, but the static pressure is catching up to the total pressure. What this is telling us is that as we increase the restriction on the duct, more and more energy from the fan is going into creating static pressure, but we have less kinetic energy, so we're actually moving less air. This becomes more obvious when we fully restrict the duct, and how the total pressure and static pressure are almost the same. I do have some leaks, so we're moving just a little bit of air, but not much at all. So let's watch the whole process one more time. Now, remember how I said we were almost done with the ping pong balls? Let's go back to them for just a second, and we'll restrict both the inlet and the outlet this time. It looks like now the fan just can't move enough air to create enough static pressure to get either of the ping pong balls to move. But I'll just speed up the fan, and now there's enough airflow and we can create enough static on both sides to move the ping pongs. Though, it is harder when both sides are restricted. Even though in the inlet we created a low pressure or negative static pressure, so to speak, and on the outlet we created positive static pressure, it's not like they cancel out. In fact, the fan has to overcome the sum of the absolute values of static pressure in the inlet plus the static pressure in the outlet. So in this case, this fan is having to create a pressure gradient of 2 ping pong balls worth. So a restaurant hood exhaust fan in a pull configuration may have to overcome, say, a 1-inch water column static pressure created by the restriction that is the duct and the hood itself, leading to its inlet, and then no static pressure on its outlet since usually there's nothing attached to it. A push configuration would be the opposite, having to overcome static created by what's attached to the fan outlet. But then in a recirculating system, we have both. You may have, say, a 1/2 inch of static in the inlet and 1 inch of static in the outlet, but the fan would have to overcome the sum of the two. And we're not just worried about static, because typically you'll want to move a certain amount of air at that given static pressure. Say 2000 CFM at the 1.5 inches of static. This means that when we're picking a fan, we really are looking at total pressure, and understanding this relationship between static and airflow is really important. Like when we sped up the fan here, did the static and dynamic pressures increase equally? To answer this, we have to look at what are called the fan affinity laws, which are a set of laws that establish the relationship between speed, airflow, static, power, and sometimes even diameter in a fan, although today we'll skip that part. The laws can be written and manipulated in many different ways, but I'll try to keep it simple. The 3 main fan laws establish a relationship between fan speed or RPM and CFM, fan RPM and static pressure, and fan RPM and power. As you can see, fan law 1 is a linear relationship, fan law 2 is a squared relationship, and fan law 3 is cubed. And this is important because it means that for any change in speed, we will get an equal change in airflow across the fan, then a larger change in static pressure across the fan, and a much larger change in the power required to drive the fan. So let's put these laws into practice. I've set this fan to spin at 7,000 RPM measured with a laser tachometer, and at this speed and with this restriction, we're seeing about 11/16 inch water column static pressure, about 3/16 inch dynamic pressure, and we're drawing 33 watts. Remember, we can multiply volts times amps to get the input wattage to the motor, which we'll use for this example in place of horsepower. Ideally though, we'd want to measure the output power to the fan and remove any variables such as motor efficiency, but for the demonstration, this will work just fine. So now that we have these values, I'll speed up the fan by 20% to a speed of 8,400 RPM. In theory, following the fan laws, we should see the same 20% increase in our airflow, which is determined by our dynamic pressure, a 44% increase in the static pressure, and about a 73% increase in the power drawn by the fan. So let's look at what we have. Our dynamic pressure is now a 1/4 inch, and using our CFM calculation, this means about a 16% airflow increase. Of course, we're eyeballing this a bit, so it's not the most accurate. Then our static pressure is right at 1 inch, which is a 45% increase. And finally, our power draw is right around 58 watts, which is about a 75% increase. This is all to say that even with this rudimentary setup, we're following the fan laws almost to a T, which makes sense. They're called laws for a reason. And now, to put these laws even further into practice, we had a group of R&D engineers test and balance the airflow across a commercial kitchen hood.
What we're testing is the amount of airflow promised to us by fan manufacturers is actually being delivered in a space. And if we're not getting that amount of air, balancing means adjusting the fan or adjusting the duct or dampers to make sure that we are getting that much air. And then you test again.
With the equipment installed, it's very important that we do a system check. We want to make sure that our CFM per linear foot has met the design parameters. In order to do that, we use an air data multimeter or a short ridge. We're measuring the velocity in feet per minute across each of the filter faces. 165. In the spreadsheet, there are multiple filters that you can pull down. So you identify the filter, the number of filters, and the length of the hood. Okay, so we're going to do a 3 average, 168. Moving on, filter 4, 148.
Through our first iteration of our test and balance, we discovered that we are at 168 CFM per linear foot. That does not meet our design specifications.
Yep.
We're currently at 30 hertz.
30 hertz.
So what we're going to do now is use some calculations, the fan laws, to increase our CFM per linear foot.
Right.
And what's the target for our CFM per linear foot?
200 CFM per linear foot.
200 CFM per linear foot.
Using the first fan law, we know that CFM directly correlates to motor RPM. So we can calculate that our new frequency for 200 CFM per linear foot should be closer to 35.6 hertz.
Okay, set 35.6 hertz.
191. 196.
So we're at 196 CFM per feet.
196.
So after changing that on our VFD, we now have a new CFM per linear foot at 196, which is a lot closer to what we expected from our design parameters, and now we know that our exhaust system is properly tested and balanced.
So how does this all work? How can a fan create a pressure gradient that sucks in air and pushes it along for a useful purpose? A lot of it has to do with this guy. Remember him? Bernoulli's law sets the relationship between speed and pressure in a fluid, any fluid. And in an earlier video, we went through great detail explaining how this works with liquids, but all the same concepts apply to air.
So when we're talking about fans, you can't forget about Bernoulli. One thing that Bernoulli established was that where you have high velocity, you have low pressure. And where you have high pressure, you have low velocity. It's the exact reason why airplanes fly and baseballs curve.
There's nothing like a counterintuitive experiment to show this in action. When I turn this blower on, it's moving a lot of air within this duct. And you would think that when I constrain the duct further down, the pressure within that constriction would increase further. But it actually does the opposite. The pressure in here becomes lower than atmospheric pressure, and so the ball goes up. The explanation is simple. In order to fit through this restriction, the air has to speed up, and it's trading all that static potential energy for kinetic energy. And I lied when I said it was simple. There's actually a lot of debate on why exactly this happens. But the fact of the matter is, it happens. And the Wright brothers knew it. Together, they developed wind tunnels to study this effect and leverage it to make the flyer fly. So this is a homemade wind tunnel. Not completely alike the one the Wright brothers developed in order to understand and perfect how the flyer's wind worked, but similar enough in principle. And while my first tests looked something like this, it didn't take long to get a usable result like this. So let's talk about airfoils. An airfoil is a device designed to produce lift with a minimum amount of drag. Birds showcase the best airfoils around, but airplanes use them as well as helicopters and even fans. Here's a NACA airfoil. The numbers correlate to specific values for the geometry of the airfoil. As you can see, we have a rounded leading edge, a pointy trailing edge, and a big curve on top with a relatively flat bottom. The air reaching the leading edge will split into two paths. The path on the bottom is pretty direct, and the air maintains a constant speed throughout. The path on top is longer due to the rounded shape, and since it's longer, the air has to speed up in order to travel around it. Now, we know from Bernoulli that when the speed of a fluid increases, its pressure decreases. So we've essentially created a pressure difference across this airfoil, which on its own creates lift upwards. We'll call this lift method number 1. But there's another way to create lift, and that's by changing the angle of the airfoil relative to the wind. And this angle is called the angle of attack. With a higher angle of attack, we're forcing the air to deflect downwards. And following Newton's third law of motion, we know there will be an equal force upward. Let's call that method of lift number 2. The airfoil shape is designed to try to keep the air as laminar, as in smooth and straight, and nicely attached to the top of the wing as we increase the angle of attack. And the thicker the airfoil, like this one's pretty thick, the better it is at doing so. But there's always a limit, and we've reached it. This is called the stall, the point at which the air detaches from the top of the airfoil, creating turbulence and greatly reducing lift, since we're no longer deflecting the air from the upper surface downwards. Most airfoils reach stall around 15 to 20 degrees angle of attack, so this thick airfoil did quite well. But there is a downside to having such a thick cross-section, and that is drag. In aerodynamics, drag is the name for the forces that oppose the motion of an object through the air. For example, the air has to flow around this airfoil, right? So its natural path is altered, and that takes energy. The air then comes back together, and one of the best indicators for airfoil drag can be seen in the air leaving the trailing edge. If we have a lot of turbulence, that means a lot of drag, because it took energy to disturb the air, and that energy will oppose the motion of this wing through the air. It'll want to pull it back, so to speak. In contrast, this is something closer to what you'd see in a commercial airliner, which creates less lift but is more efficient due to reduced turbulence, which I think is clearly visible here. And when I mention efficiency, I'm talking about the ratio of lift to drag, and the higher the better. So, what approach did the Wright brothers take for their flyer? They tried a few things, but in the end it looks something like this. This profile is very good at creating a lot of lift, at the expense of extreme drag. But remember, the flyer averaged less than 10 miles an hour, so lift is what they were after. Not only is the top curve pretty extreme, but the bottom is also curved in a way that directs air downwards, even with a neutral angle of attack. So it was very good at high angles of attack, but look at all that drag. We've all seen airplanes fly, right? There's no question that these airfoils are working. But recently, there's been a bit of a debate of how it all actually works. A lot of people are questioning our fundamental understanding of flight. And the reason why is because of what I'm about to show you. This is a completely symmetrical airfoil. The top surface is shaped exactly like the bottom. And there's a bunch of planes flying around using this design. At this neutral angle of attack, it creates zero lift. So the whole Bernoulli method doesn't really apply here. But when we increase the angle of attack, the second method still creates lift. We're still deflecting all that air downwards. So then why is the wing rounded at all? That's just to try to keep the airflow attached as much as possible and reduce drag at high angles of attack. But it doesn't have to be round or any shape in particular. If you've ever stuck your hand out the window while driving a car and angled it up, you can feel that force pushing your hand up. That's lift you just created with your non-airfoil shaped hand by simply deflecting incoming air downwards. So with that, here's a completely flat airfoil. It works, and sure, it stalls at a lower angle of attack and creates some turbulence off the trailing edge, but it still works. And although we're not using the Bernoulli method to create lift, just propelling the air downwards still creates a high pressure zone below and a low pressure above the wing. Now, let's take these concepts into some different kinds of fans, starting with axial fans. An axial fan is called that because the air flows parallel to the axis of rotation. These fans are very commonly used as household fans because they're good at moving a lot of air efficiently, like your ceiling fan at home. Typically, these have a flat blade profile and they just deflect the air downwards, upwards, depending on which direction they spin. The big brother to these fans are called high volume, low speed fans, or HVLS.
It was originally developed for the dairy industry. In the summertime, you want to keep cows cool to boost milk production, and farmers were looking at ways of how do I cool this entire barn? So HVLS fans, I think, were born out of that concept. If you look at the airflow patterns out of an HVLS fan, it's literally a column of air that moves from the ceiling to the floor and then spreads outward along the surface of the floor.
When comparing HVLS to a smaller fan, they may both be able to move the same amount of air, but to do so, the HVLS moves the air very slowly, while a smaller fan will have to do so much faster. The faster that air moves, the more turbulence is created along the boundary of the column of air. So in comparison, HVLS uses much less energy per CFM. This, combined with very low noise, has made it a popular choice, especially in large spaces, serving well to provide a nice stream of air for evaporative cooling in the summer, as well as destratifying or mixing the warm air that naturally rises towards the ceiling in winter. HVLS fans made their way into many industries far beyond dairy production. And here's what our blade design looks like. You can see it's a lot like some of the airfoils we just studied. So does that mean these blades are trying to fly? Well, essentially, yes. That's how an axial fan works. But of course, the whole blade assembly is attached to a shaft, and although it may flex a little, it's going to remain relatively stationary in this axis. That means that all the lift generated by the blades will result in air moving downwards. So let's look at the profile in the wind tunnel. And you can see it's a bit of a mix between a modern airfoil and the Wright Brothers design. Up top, we have a heavily curved section, which will create low pressure using the Bernoulli method. We have a nicely rounded front and a thick cross section here, which gives the blade a lot of its structure, and a heavily curved bottom which pitches down to deflect air downward using the Newton method. So the whole airfoil is working together to create low pressure up top and deflect a lot of air downward efficiently across a large range of air velocities. And this last part is important because if you think about it, since the blades can be so large, like 24 feet in diameter, the speed of the blades close to the hub or the root is much lower than out towards the tip. And we want the whole fan to be working for us as much as possible. Although we definitely do optimize for the outer sections of the fan to be the most efficient and stall-free. Now let's talk about stalls in axial fans for a minute. We already determined that stalls are caused by exceeding the critical angle of attack to the relative wind. In the wind tunnel, the relative wind is perfectly horizontal. And you might think that's exactly how an axial blade would encounter the wind. But no, not really, because the blade itself is also creating airflow downwards. That's the whole job of the fan after all. So then the resulting airflow direction, and thus the resulting angle of attack, is dependent on these two vectors. It's not uncommon to depict the angle of attack like this then, a vector derived from these two velocities, meaning the angle of attack can sometimes vary quite a bit. Interestingly, in a large fan with a constant blade angle like the HVLS, the angle of attack through the blade tends to stay fairly constant. Although the speed of the blade is dramatically higher at the tip compared to the root, so is the speed of the airflow downwards. So the resulting AOA stays about the same. With that in mind, it's still important to set an appropriate angle of attack and to actually test different configurations.
Just like an airplane wing, if you make that angle of the blade too steep, the air starts to separate and you just start to lose performance. We looked at the max RPM of those fans and the max tip speed and designed that angle around that tip speed.
Another thing to thoroughly test are the wing tips. We want the column of air to remain straight down. That way, if the fan is mounted high above the floor, we can still effectively maintain airspeed down towards the ground and produce a diffusing effect along the floor. So how the blade tips handle the air is crucial, and to understand why, we need to look at span-wise flow. Span-wise flow is any flow that moves along the span of a wing or blade. Here's our HVLS profile mounted on its side. And you can see here that because the bottom surface is creating so much high pressure, some of the air is moving sideways, span-wise, flipping all the way around to the top where the pressure is low. This also creates these vortices, which have the added negative effect of increasing drag, since again it takes energy to swirl the air around like this. When you have a lot of span-wise flow, it's impossible to keep the column of air straight, since the air is already getting flung outwards radially along the span of the blades. And so, a lot of the energy of that airstream is dissipated before even reaching the ground. So, to alleviate this effect, well-designed planes and fans use modified wingtip shapes to reduce how much work the airfoils are doing right towards the tips. Alleviate being a key word because you can never fully overcome this problem. Here's a shot of our own fan tips. We're still creating some vorticity, but reducing the span-wise flow and vorticity as much as possible is still crucial to reduce energy consumption and improve how we deliver the air.
We did a bunch of different designs and CFD analysis and saw how that affected our airflow. Some blade tips were causing the air to go out in a conical shape like we talked about. That's what led us to having that cut on the discharge side of the blade as it goes out to the tip. That basically allows us to prevent any of that air from slinging outward. And when you run one of these fans and you walk under it, you can feel a defined line. As soon as you get underneath the blade tips, you'll feel that air blasting down, but if you take a step back, you're not feeling that downward blast anymore. So that's something that CFD analysis really helped with. Noise is another one. Trying to basically create the most aerodynamic shape of the blade tip because that's going to be the location that the velocity is the highest. So keeping that as aerodynamic as possible keeps the noise down as well. And then after we did CFD analysis, we actually did a bunch of different 3D printed tips to test and try them out and verify, CFD analysis is great for theoretical, but we like to, test everything out here and make sure that real world applications, it works well.
In order to spin slowly and deliver the required torque, HVLS fans use a reduction gearbox between the motor and the fan. Now, if you take the same design, reduce the size a bit, and remove the gearbox, you have your traditional propeller fan. These are to this day the most commonly used type of fan, used to exhaust hot or contaminated air from all sorts of industrial and residential applications. With the introduction of higher torque, lower speed motors, they can often be driven directly and efficiently without the need for belts and pulleys. And since the structure is required to hold all the components together, it's easy to add a Venturi housing, which does away with all the issues related to the tips of the blades common to HVLS. With the housing in place, the blade tips can retain their shape without creating massive span-wise flow and tip vortices. This rounded Venturi shape smoothly directs the airflow towards the blades. Although smaller than HVLS, these prop fans are still relatively large in diameter, thus taking advantage of the performance benefit of moving a lot of air at a slower speed. But what they're not good at is overcoming any amount of static pressure. And you can kind of see why. We have these huge gaps in between the blades, making it very hard to build up much pressure at all. So then we move on to the next category of axial fan, the TubeAxial fan. They're called TubeAxial due to the cylindrical tube surrounding the blades. Much like in the prop fan, this tube helps the performance of the fan by preventing air getting slung outwards. The longer tube and also larger fan blade area allows the TubeAxial fan to overcome some medium or mild static pressures. And finally, we have the VaneAxial fan. These fans are very good at efficiently overcoming higher static pressures while still moving large volumes of air. We use this design for our HVAC outdoor fans, so let's take a look. Axial fans, even ducted ones, tend to swirl the air as it passes through the blades. Just like with tip vortices, this swirl is wasted energy. What makes VaneAxial fans special are these guide vanes that straighten the airflow, thus converting the otherwise wasted rotational energy into useful work in the form of straighter, faster airflows. There's a few other details that also help this fan create higher pressures, like the fact that the hub takes up a significant ratio compared to the fan blades, a common trait among this category. The blades cover a large area of the fan with very small gaps in between, and the fit between the blades and the cylindrical housing is very tight. You'll also notice that the blades have a twist. The root of the blade is angled more steeply than the tip. This is to equalize the angle of attack along the blade, since unlike the HVLS, the air moving through this fan will be at about a constant speed throughout. But once again, the linear speed of each blade section increases the closer you get to the tip. And guess what? This twist is also seen in propellers and jet engine blades on just about every airplane you've seen or flown in. The basic airfoils pioneered by the Wright Brothers were developed into not just better wings, but more efficient propellers, jet engines, and fans, all intertwined. But it's not all rainbows and roses, because as you could tell from all these wind tunnel demos and illustrations, axial fans can be very finicky, especially when trying to overcome a lot of static pressure. A VaneAxial fan can do it, but if the velocities are not just right, we run the risk of stalling the blades, which means even the best of axial fans tend to operate in narrow windows or at just generally lower static pressures. But don't worry, there is an alternative. The world is a weird place sometimes. And right now, it's one of those times. Because this is the only video I could find that's dedicated to the life of this Russian lieutenant general. And I'm not even sure that this is the right portrait of him, but you know, for 29 bucks, I can get him framed and put up on my wall like this. Here's the entire Wikipedia article on him. Yes, you're looking at the whole thing. So let's read it together. Okay, Alexander Sablukov, Russian Lieutenant General, engineer and inventor. Okay, and he's credited with the invention of the centrifugal fan in 1832. No big deal, right? Centrifugal fans, also just called blowers, are an entirely different category of fan, and they're very, very good at moving air against a higher resistance, against a high static pressure. That's why I used one for this demo. A tiny axial fan would never be able to raise the pressure this much.
So if you were to put an axial fan in a modern RTU, for example, you will move a little bit of air, but you can spin that fan as fast as you want, but you'll never be able to overcome the resistance of a ducted unit with coils and filters and dampers and things like that.
So how do they work? At the heart of the centrifugal fan is the impeller wheel. This is the part that is driven by the motor. It consists of a bottom blade, a set of primary blades, the top blade, and a hub. The job of this wheel is to do work on the air by imparting kinetic energy onto it. And it does it in two ways. Let's take a very simple looking wheel and just focus on the blades. Imagine a small pocket of air sitting between two blades. As soon as the wheel starts to rotate, that pocket of air is going to start experiencing centrifugal force, which will start moving it outwards. They say centrifugal force is a pseudo force, but I mean, have you ever been in a merry-go-round? Right, so centrifugal force is the first method used to accelerate the air, flinging it outwards in all directions. Once the air leaves the wheel, there's now low pressure and room for more air to come in, and the cycle continues. So what's the second method? Take a look at the path the air takes when it exits this wheel. If centrifugal force was the only thing at play here, the air would exit completely radially like this. But the blades are actually pushing the air right until it exits, deflecting it and changing its path a bit while adding some extra velocity. The angle at which these blades sit will also have some effects on this. So far we've been looking at a centrifugal wheel with radially oriented blades. This is a bit of a middle ground. There are also wheels with backward curved or backward inclined blades, and even forward curved ones. At an equal size and speed, forward curved blades will move the most air while creating the most amount of pressure because they deflect the air the most. But this comes at the cost of more turbulence and inefficiency because the air is making a steep turn. On the other hand, backward inclined blades will move less air while creating less pressure, but with much more efficiency as the air flowing through takes a much straighter path. And radial blade fans are right in the middle. Here's a closer look at the paths taken by the air in a backward inclined wheel versus a forward curved one. The latter putting more energy into the air by deflecting it more at the expense of efficiency.
We actually have used a mixture of backward incline and forward curve fans over the years, and backward incline, backward curve are more commercial applications where you have to move a higher level of air but against a higher resistance. They're also typically used in more industrial or robust applications. For example, grease exhaust, that is a very common use of backward incline fans. And in HVAC equipment, high-end HVAC equipment will use a lot of backward incline wheels.
Our wheels use simple backward incline or curved blades to direct the airflow. Other designs can incorporate an airfoil blade as well. However, these blades are not flying, so to speak, not in the sense that they do in an axial fan. In fact, it's almost like they're upside down because the longer airfoil surface is actually on the high pressure side of the blade. This is completely backwards from a traditional airfoil. So yes, an airfoil blade can be slightly more efficient than a curved or flat blade. But the difference is small because the blade isn't flying. Now let's talk about the main components surrounding the wheel. To introduce air into the center of the wheel, we use an inlet cone or Venturi. This piece is shaped to maintain laminar flow and direct the air to start turning towards the blades. Note that the wheel's bottom blade carries this shape over, and the two are designed to work together. Even without the inlet in place, this is the natural shape the air wants to take, all on its own. But why not just plug a smaller duct directly into the wheel? Well, typically for a given size centrifugal wheel, the amount of air moving will be larger than a duct that size could handle without a serious increase in static pressure. So it's just best to use a larger duct along with a Venturi inlet. Also, the reason it's called a Venturi is that the whole inlet converges into a smaller space, thus increasing the airspeed within it, which also means a decreased pressure. This lower pressure when compared to the duct upstream helps draw the air into the fan and gives us a higher pressure delta to work with. Since the path between the blades is diverging, we do regain some of that static pressure right away within the wheel. The wheel itself will then propel the air outwards in all directions. So what do we do with that air then? The most common design incorporates what's called a scroll housing. The scroll housing is designed to collect all those airstreams and unify them into a single one, which will exit at right angles to the axis of rotation of the wheel. The diverging spiral shape of the housing is very specifically tuned to efficiently convert the kinetic energy of the airstream leaving the wheel into pressure, with Bernoulli at our side once again. Diverging duct equals more pressure. You'll also see that the width of the scroll housing is actually quite a bit wider than the primary blades. Typically, it will be about 75% of the wheel diameter. And this is to allow even more expansion of the airstream as it leaves the wheel. Remember, airspeed often means turbulence and associated losses, so converting that energy into static pressure right away makes a lot of sense here. Another design commonly used for exhaust fans incorporates a spun housing to redirect the exiting airstream. In order to maintain efficiency, the transition is smoothly shaped so that the air follows a large radius turn before discharging to free air. And this example shows a general application downblast fan. But when any type of grease is involved, like in a restaurant kitchen, you really don't want to discharge all that grease-laden air right onto a roof, so an upblast fan like this one is more appropriate. This fan is designed to collect some of that grease and can withstand moderate cooking temperatures. However, when cooking with something like solid fuels, the temperatures can be too high for all these aluminum components. So we typically specify a utility set. This type of fan uses an all-steel scroll housing with an optional steel wheel, both which can withstand much higher temperatures. The whole design can also handle higher grease and soot levels. First off, the wheel and inner housing are easily accessible for periodic cleaning of all this grease, which is crucial for maintaining performance and safety. And speaking of performance, this fan takes a small hit because instead of smooth exhaust transitions, we purposely place these surfaces and tabs at steep angles to catch more grease. While the air can make the turns somewhat smoothly, the grease particles are heavier and thus have more inertia, so they get flung out of the airstream and into the walls and tabs. Then gravity forces the grease down into a drain. So there are times where we have to consider other factors beyond performance and efficiency. And that leads us to our last kind of centrifugal fan. What if we just remove the scroll housing and place the impeller wheel within the confines of the equipment itself? We refer to this configuration as a plenum or plug fan, depending on how the motor is mounted. And that's what we use inside our own HVAC systems. Here, the conversion from airspeed to pressure happens very quickly, as the air is immediately allowed to expand within the large cabinet.
One requirement that I had was we needed to have a direct drive fan. And while you can put blowers in a direct drive orientation, it's a lot more challenging to do that, just from a engineering standpoint and a structural standpoint. So that backward incline and backward curve type wheel in a plug or plenum style is easy to attach to a motor, and it pressurizes the entire cabinet around the wheel. So it's easy to mix that air and to spread it around on to heating elements and electric inserts and things like that. It pressurizes the discharge of the fan, and it spreads air out a little more uniformly. You could argue that the velocities coming off of that plenum or plug style fan are in all different directions, and sometimes it's very close to the cabinet wall. So yes, there are some efficiency losses there, but what we have determined is even with those losses, being able to apply that wheel in a direct drive application and mixing that air on the leaving side of the fan is much more important and offsets those minor energy losses.
One configuration where the plenum or plug style fans start to show increased losses is when the cabinet fits a lot closer to the fan wheel, like in this square inline fan. The air leaving the wheel has very little time to diffuse, and all that velocity results in a very energetic and very acute change in direction. The air then bounces back against the incoming air, and this ends up creating more turbulence and loss of performance. But what if you could have a fan wheel that directed the air at an angle to mitigate these losses? Enter the mixed flow wheel. Mixed flow wheels combine some of the best characteristics of centrifugal and axial fans, energizing the airflow both centrifugally and axially. This is a model of our own wheel. You can see it still uses a backward incline setup, though now the blades have angles to them to maximize performance and strength. From this perspective, you can see that the air is flung out in a very similar way to a centrifugal wheel. But when looking at the wheel from the side, we have this new taper, and the blades have this additional angle. This is the angle that propels the air in the axial direction. When you combine both the centrifugal and axial forces, the resulting airflow moves not perpendicularly, but at an angle, which is much more efficient in a plenum or plug configuration. Now, since mixed flow wheels add in the axial element of flow, they're superior to centrifugal wheels when it comes to delivering airflow. But they can't quite match centrifugal wheels when it comes to pressures, at least not at equal speeds.
One practical limit of fan wheels is max RPM. If you look at our mixed flow fan blades, they have angles on them. And a lot of competitors will be straight or flat, or sometimes they'll have a backward curve to them. And what we found is we wanted something with bends on it so we could add a lot of rigidity to that fan wheel, and we can spin that wheel much faster. For example, a backward incline wheel, aluminum wheel, if you spin it too fast, the blades will actually just fold in half. The wheel will just collapse. So while mixed flow fans aren't quite as good as handling the static pressure of a true backward incline fan, we can overcome that by spinning the wheel much faster, moving a lot more air against a lot more pressure.
If we take a look at one individual blade itself, actually pretty complex as far as the bends going on with everything. But one thing to note is if I actually create a flat view of it, each bend is a dotted line, and that bend is parallel to the outside edge of whatever side you're bending that from. So basically we had to make it so that it was a sheet metal part that could be cut and then bent on a brake press. It was before a lot of the automated equipment was existing. As it's spinning, we needed to make sure that the tip of the blade is pretty tangent to the inside of this wheel itself. And then as you fall to the outside of the wheel itself, our angle changes. So you don't have one abrupt change of air. The air as it's getting scooped is following the path of the blades in between the blades. So it's actually the working side of the blade is actually the back side of this blade here. So it's running across that. And if you go to too steep of an angle, what happens is, depending on the velocity of the airflow, the RPM of the wheel, it'll actually the air will break off the edge of that blade, creating a lot of turbulence and making the wheel quite ineffective. So we had to do a lot of different tests to make sure that we didn't run a fan where basically the performance would drop off.
In the next video, we'll look at fan performance curves and all the ins and outs of choosing fans and motors for peak performance and efficiency. It's a bit of a detailed one, so come take a deep dive with us, and as always, thank you so much for watching.